All right, hi. So here's the thing. I think it's important to follow the rules. So what I'm doing right now, if the class reps are online, sorry I'm late by the way, you want to tell these people that are logging on from outside the University of Zambia that they should log in using their own email addresses. We've been over this a couple of times now. I suppose makes little sense in going around in circles. All right, great. So on with it. Let me just open up the presentation slides and then we can start. I do hope you can hear me.
Yes, we can.
Okay, great, thanks. All right. This is wrong. It's not interaction number 6. Should change this somewhere. I hope you're fine. I hope you are keeping safe, and I do hope you are ready for upcoming assessments, I suppose. ClassRep, if you have access to, or ClassRep, if you have access to WhatsApp, you want to tell these characters to log on using their other assigned email addresses, please.
Okay. Yes, I've just done that.
Okay. Sorry about that. Just quickly. And it's a trivial thing, but always nice to ensure that things are in place or in order. Right. Great. So today's interaction is really going to be just a quick walkthrough of lecture series number 7, and then again just a sneak preview of what to expect in lecture series number 8 and number 9. Now, the reason we're having, I guess, a preview of lecture series number 8 and number 9 is because lecture series number 8 and number 9 are actually closely related to each other, right? It turns out that before we can actually have a discussion of the input, the so-called input-output subsystem, it's always a good idea to contextualize why it is there in the first place, right? And its role is to provide an interface between peripherals and the computer system, right? So which is why our walkthrough is going to involve 8 and 9. And 8 is a relatively short lecture series, really, which is why both 8 and 9 are going to be covered next week. But I'm going to start off with a few announcements for those of you that, and I know, right, there are a lot of you in here, those of you that have not yet figured out what's going on, right, still getting emails about the same things over and over again. But if you check the calendar, what you will notice is that there are 2 key activities, right, aside from our normal offline screencasts that are going to be available next week. We have, actually this week we have assessment quiz number 6, right, which is Friday. I guess people are aware about this. It's going to be based on lecture series number 7, right, the CP instruction execution cycle essentially. But besides that, we also have a scheduled class theory test number 1. This is on the last day of class for term 1, right? Now, there's a thin line, clearly there's a thin line between term 1 and term 2 here. If you have bothered to look at the email that I forwarded or the document that's available on the UNZA website, what you will notice is that we transition seamlessly into term number 2 the following week after we're done with term number 1. Do you understand what I mean here?
Yes, sir.
Yeah.
Yes, sir.
No, can you repeat the same thing again, sir?
No, sir.
What I mean is, if you go to the UNZA website, like I'm doing right now, everybody has access to the UNZA website, right? Second nature here. And
so
if you, yes?
If you are presenting anything, I cannot see. Or if there's anyone having problem. Yes.
Oh, I do apologize for that. My fault. I'm just going to go back here. You know, this is irritating. I'm just going to deny entry because people don't seem to want to learn, right? This is horrible. All right, great. Sorry about that. I do apologize. I'm just going to present this. All right, great. I hope you can see my screen.
Yes, we can now.
Okay, great. So I was saying, in case you didn't really, for those of you that have not bothered to access the calendar, the course calendar, or to access activities, because the calendar is actually synchronized on the Moodle, what you will notice is that we have a couple of key activities scheduled in the next coming days or next coming weeks. On Friday, we have quiz number 6. Quiz number 6 is based on lecture series number 7. Lecture series number 7 is centered around the CPU instruction execution cycle, right? But besides the quiz, on the last day of class for term 1, we have class theory test number 1. Now, I was saying, before somebody was kind enough to remind me that the screen was not shared, that if you look at the revised session dates, right? If you go to the UNZA website and you go to the revised session dates, currently I think it's the second announcement or something, what you will notice is that we seamlessly transition into term number 2, I think, unless if I'm mistaken here. All right, last day of class is Friday, 24th July. First day of class for term number 2 is Monday, 27th July, right? Last day of class, Friday. The following Monday is first day of class, term 2. So really, I mean, I don't even know why they came up with term number 2 here. There's no term number 2 here. So there we go. Last day of class, which is the 24th, we have our class theory test, right? Now, the thing with class theory test number 1 is that it's going to be based, I know in the last communication I sent through with regards to the scheduled assessment itself, I had mentioned that the test was going to be all the way up to computer memory basics. Looking at the time we have left, it will not be possible for us to include computer memory into class theory test number 1. So with that being said, class theory test number 1 will cover everything all the way up to the input-output subsystem, which ideally is lecture series number 9, right? Not number 8 here, number 9. Are we together? So what this means, also, what you will notice is that unlike what we had previously discussed with regards to the tentative schedule of the assessment, we will not have 4 tests, we will have 2 tests, right? Because of the confusion that's going on here. In an ideal case, we're supposed to have written 2 theory tests in term number 1 and then 2 theory tests in term number 2. But alas, is this going to be 2 tests? We'll try and see if we can keep up with the quizzes so that we write all the 20 quizzes. But it changes very little here because if you remember, if you get back to your course syllabus, what you will discover is that the assessment are based on the weighted averages of whatever items associated with the different categories. So even if we were to write 10 quizzes instead of 20, we still get the weighted average because we know that 20 marks allocated to the quiz and then there's 30 marks allocated to the test. So whether we write 1 test or 2 tests, we just evenly distribute the scores. Does that make sense? Okay.
Yes, I think.
Okay, great. And then I'm not really sure if people need clarification on quiz number 4. I did notice that some people asked questions and then I responded, but I was uncertain as to whether some of the concerns that people had were addressed when I responded or not. For some of you, I think I responded individually to you. There was especially a concern around the readjustment of the scores, right? I don't know if that makes sense. If you, well, I suppose we wouldn't be able to figure out, but it turns out that one of the questions, the solutions for one of the questions was not correct. And so we had to regrade the quizzes, which is why for some of you, for the vast majority of you actually, your scores went up, right? But for some of you, your scores were sort of like readjusted in the opposite direction, I suppose. So you lost a mark or like half a mark or something, right? So it's with regards to quiz number 5, not number 6 here. And then I thought it was interesting that the vast majority of people actually, now this is irritating, so, you know, I don't know who this McToffee is, you know, and memory, right? Here's the thing. If you want this to work, if you haven't figured out what's going on, if you're struggling with a number of things going on, my advice to you, like I said many days ago, weeks ago, is follow the instructions. This is what you do in life. If you have no idea what's going on, you follow the instructions, especially if those instructions are coming through from a guide. You just have to follow through the instructions until you get to a stage where you're able to figure out what's going on. But you don't want to follow this. You're not attempting the tutorial questions. You're not accessing the course resources, right? I mean, here's the thing. I'm coming to that actually. I know that the vast majority of people got, I guess, above 4.5, which was pretty good and decent, I guess. But we still have these few people that probably need to pull up their socks. Now my assumption here, I guess, would be that these people just didn't read, right? They didn't bother to read. Here's the thing here. Even if you pass this, but if you got a relatively low score, right? Even if you're part of the final and you got a relatively low score, why is it that you're not accessing? Why is it that you're not bothering to access an explanation? The screencast as an explanation as to how the marks were awarded, the solutions, right? Only 9 people have bothered to access that resource. Is there a reason why this is happening, by the way? Or was the PDF document that was uploaded on the Moodle sufficient for your needs or something? I don't know if someone has a response to that question, or is the question not properly phrased or something? Was it not very clear? Francis, class rep, did you bother to play back the screencast so that you could understand why you lost marks in quiz number 5? I don't know if Francis is online or not. Thelma, did you bother to play back the screencast, providing an explanation as to how quiz number 5 marks were awarded? Did you bother to play back that screencast, Thelma?
Yes, actually, sir. I'm one of those people who actually get a better understanding through the screencast. So I do actually play the screencast for each lecture.
Well, there's a reason why I'm asking this, right? I have no idea if people are struggling to access these resources. These resources are available on Moodle. We've gone through the trouble of properly curating these things, right? If you notice, the way this thing is structured, this is different from the other courses. I don't have this course. This Moodle course doesn't have the obscure setup where everything is embedded within a separate like section, similar to this. Everything is out in the open here, properly organized, right? All of the video screencasts are tagged, right, for each lecture series. Now, the question I have is, why is it that if you scroll down to lecture series number 6, which is where you have quiz number 5, why is it that only a few people, only 9, right? Only 9 out of 80 people access this resource? Is there a reason why this is the case? This is what I'm trying to find out. Okay, fair enough. Is there anyone who is struggling to access the resources on the Moodle, who's like a bit lost? Where is this information coming from? Is anyone struggling to access the resources on the Moodle? This is a problem here, right? This is the problem. I mean, if you want this thing to make sense, if I were you, right, I'd at least make an effort, make that effort to actually do this. I can actually drill down to show you what I mean here. I can go here and just try and see if I can access this thing actually. This is what I'm talking about here, right? 8, and perhaps one of the 8 is actually me, because once I upload this, oh sorry, that's not the one, it's this 12 so far. But the 12 is there because I sort of like access this resource in incognito so that I can confirm that people are actually able to access the resource, right? So this is misleading. It's actually much less than this. No, it's fine, right? It's fine. I know that on average as well, on average, we don't normally have the entire class attending this live interaction, right? Like right now, if you look at the number of people that are logged on, it's 36 out of 8. This is less than half the class. And the question I have is, if you're one of those who's unable to attend this live interaction, and I have no issues if you're unable to attend this live interaction, right? That's fine, I understand. If you notice here, I downloaded the load shedding schedule myself. I'm affected by this confusion, right? So I understand that some people might not have access to data bundles at that point in time. And so what we do in all of these different activities that we have in class is we archive, we record the interactions, and we make them available. So the question I have for you is, why is it that people are still not accessing the recorded interactions? If you look at the most recent interaction that we had, what the hell was this? The 17th, I think. I don't know if it was the 17th of June when we had this interaction. Yeah, it was on the 17th, right? Why is it that still you have the vast majority of the class? This is far less than the class actually, right? Anyways, whatever works for you. If you're able to follow through without consuming these resources, that's fine. But here's the thing, right? The way the system is set up is you are tested at certain points in time. You're tested for this particular course, you're tested by way of quizzes, you're tested by way of class theory tests, and then you're going to be tested by way of the exam. The only way you'll be able to perform better in these assessments is if you just follow through with the instructions, consume the lecture resources that are made available to you. But hey, whatever works for you anyway. Okay, so that's that. I just thought we'd do a quick walkthrough here. Again, if you look at if you look at the people that have managed to play back the lecture series that quiz number 6 is going to be based on, you can see here, but maybe there's a bit of there's a bit of hope here, I suppose. You know, there's some hope here because I don't know if you can see this, but we have at least almost 50 views here, almost 60 views for almost 60 here, almost like hovering around 60 somewhere there, which is good enough. But I know that some of these views are like coming from the same people, right? So still, this is not good enough. But my advice to you is just make sure that you at least attempt to consume these resources. All right, so what you would have noticed, right, and I'm expecting questions on this thing as well, the quiz on Friday. What you'd have noticed is we sort of like started our conversation by trying to latch on to this idea or concept of how software is actually executed by the computer. So we introduced this idea in lecture series number 5 when we looked at computer software. We made mention of the fact that in an ideal case, what you typically do for you to use software is you first of all download the piece of software, then you install it on the computer. And it turns out that every time you execute the piece of software, like I'm executing Ocular right now, that piece of software is going to be loaded into a staging area we are loosely referring to RAM, right? For the vast majority of the time, it's usually RAM, but in certain instances, it could be ROM. It is from RAM or ROM that individual instructions associated with that piece of software that is loaded into RAM are executed by the CPU. Now, the execution, we said, is done in sequence, one instruction at a time, right? And it makes sense really, because if you remember our discussion of the stored program concept, we said that this thing is so powerful, right? This ideal concept is so powerful because it allows us to convert this device, this electronic device we're calling a computer system, into this generic, useful artifact. Generic in that people from all walks of life and people from various domains can actually use it for different things. And it's possible to do that. It's possible for you to use the same piece of hardware for different things because you can swap out computer software depending on what you want to use that piece of hardware for at that point in time. But as they are using a particular piece of software, individual instructions associated with that piece of software are executed one at a time, right? So they're fetched from RAM, taken to the CPU for execution, one at a time. And so what we did was, in lecture series number 7, we went through this cycle, the execution cycle, went through the various stages associated with this execution of those individual instructions. Remember, the cycle is associated with the individual instructions associated with a piece of software. So if you have a piece of software like Chrome, which has, let's say, thousands of lines of code, for instance, or instructions, what we're saying is, as you're using Chrome, once you load Chrome into RAM, individual instructions associated with Chrome will be executed on the CPU, one at a time. Now, this makes sense, right? Because we again made mention of the fact that a typical central processing unit will normally execute instructions at a certain predefined rate. These days, that rate is in gigahertz, right? Giga is like billions, right? So even though you are executing these instructions one at a time, you're executing them at a very fast rate, so much so that the human brain is not able to kind of like figure out that the execution is done sequentially, one instruction at a time, because it's done at a fast rate. Yeah, so we went through the process, the instruction execution cycle. We discovered that the so-called instruction execution cycle is actually composed of 4 key stages. Now, again, this is like just a conservative approximation of the stages. In certain literature that you find online, you will probably not come across, or you probably not find step number 4 there. But it makes sense because in certain instances, you'd want to store the results of the processing on the CPU. Right, so 4 key stages that begin at the point in time when the instruction is fetched from main memory. Boom, instruction fetched here. That initiates the instruction execution cycle. And we discovered that really, once that instruction is fetched, there are a couple of interesting things that happen here. Because these instructions can potentially result in a different outcome, one of the things that the CPU needs to do is it needs to figure out what needs to be done, right? So the instruction needs to be decoded. Once the CPU figures out what needs to be done, once the decoding is done, we discovered that then the instruction is executed. In almost all instances, the execution results in some value that needs to be stored somewhere, right? This is why you have step number 4, right? So 4 basic steps, right? Fetch, decode, execute, store, right? In some books, perhaps that you've been reading, you've likely come across this. A picture like this, right? Slightly more advanced, but if you look at these different phases here, you have IF, which is instruction fetch, ID, which is instruction decode, EX, which is execution, MEM, which is like storage, right? You're writing back to memory, write back, right? So it's one and the same thing. 4 phases: fetch, decode, execute, store, right? And what we also did was we further drew down because we started off our discussion by looking at by abstracting the functionality of the different steps, right? And we drill down these different steps to try and gain a detailed understanding of which CPU subcomponents are responsible for the different stages associated with instruction execution cycle. Right, so we discovered really that, so
We can't get you, sir.
So fetching of this memory. No, pause. You can't get me?
Actually, you're breaking up. That's what you meant to say.
Yes, sir.
That's what...
Okay, sorry about that. Am I still breaking up? Let me see if I should swap. Am I still breaking?
Yes.
Okay, just give me a second. I'm sorry about that.
Hello, guys. Can you get this up?
No, he's cut. He's cut.
No.
Is it Thelma to write? Thelma, you should write a message to this. I might come back and start saying that we didn't tell him that he has stopped.
Yeah, just like last time.
How is my connection now? Hello?
All right.
It's clear. It's clear.
The network is poor.
Yeah, I'm gonna pause before I continue here. Let me see if I can identify someone who is serious here. Austin, can you clearly get me?
Yes, I can get you clearly.
Okay, great, thanks. All right.
But we were unable to see what you are presenting.
Yeah, that's because I disconnected and then I have to reconnect again. So I just wanted to confirm before I reconnected. Just give me a second, I'm sharing my screen. All right. Yeah, I don't know if that message is meant for me, Kennedy. I don't think I've used 70% of my data, sadly, but maybe that's you. Okay, great. So if you can see my screen, I don't know if I'm just going to see if we can double back briefly. So I was trying to latch on to. There's a bit of echo. I don't know whose microphone is still on here. Can I ask that you switch off your microphone, Brian? Switch off your microphone, please. And Sintenda, please. Great. Thanks. Okay. So I don't know if I was clear enough when I was walking through these different steps, these 4 steps here, but I was trying to emphasize this idea of abstraction, the real power of abstraction. If you notice, one of the consistent things we're going to introduce in everything we're going to discuss is centered around abstraction. Right? The golden thread, one of the golden threads in what we're doing is abstraction. So as we're discussing, as we are really studying how computer systems work, you notice that we'll be peeling off the layers of abstraction, right? And same applies to execution of instructions, right? We're abstracting, and then once we abstract these 4 layers, we further go to a stage where we had a firm sense of which specific CPU subcomponents are responsible for the different functionalities, right? This is important here, right? I guess the key takeout point for this is we should be in a position to now know the role of the different CPU components, like specific special purpose registers, for instance, what role they play, right? Why the control unit is there, why the ALU is there. It's interesting thing about the ALU, or the computer as we know it, right? The computer does 2 things. This thing you're calling a computer does 2 things: addition and subtraction. That is all. Everything that you see, everything that you do on the computer, your mobile device, whatever smartphone you're using right now, is centered around addition and subtraction. That's all. On the CPU itself, when you're executing these instructions, it all boils down to addition and subtraction, right? And those of you that were paying attention in grade school, I suppose, or maybe middle school, I think, will probably remember, right, or agree with me that if you can add and if you can subtract, then you can divide, you can multiply, right? What the ALU does really, or what the central processing unit does fundamentally is it performs what are called arithmetic operations. And arithmetic, there's a difference between arithmetic and mathematics here. So arithmetic, I guess, is more primitive. It's more primitive than mathematics here. So we now know what sort of role the different CPU subcomponents play insofar as the fetch, decode, execute, store cycle is concerned, right? And then we had fun, right? Using some hypothetical examples. Now, those examples, by the way, are more or less like, you could view them as being the equivalent of assembly language instructions. I was a bit careful not to not to use MIPS assembler, which is what we are going to look at as a case study once we cover the instruction set architecture, because I thought it was going to be slightly confusing. So what we've done traditionally is we use an abstracted form of assembler, right? So the instructions that we have, like add 104, for instance, might not necessarily be add 104, right? In fact, in MIPS assembler, when you're adding two numbers, what you would do is you use the add function, you specify the input register, sorry, the output register and the input registers, like so. So this line number 4 that you're seeing here is what addition in MIPS assembler would be like, right? And in fact, the thing you're seeing in line number 4 is the equivalent of this. It's like you're adding what is in register number 9 and what is in register number 8, add them together and then put them into register 10. But because this is somewhat confusing, what we do is when we are looking at this part of the lecture series, we abstract what is happening here, right? We abstract the gory details to simplify things, right? All right. So we went through some examples. We cycled through a few instructions to gain an appreciation of the role of these CPU subcomponents, and more importantly, the registers, the special purpose registers that are involved. So the memory address register, the memory buffer register, or memory data register, the current instruction register, the accumulators, these are all special purpose registers that play key roles associated with execution of instructions by the CPU, right? Which I thought was really fun, really. And then towards the end of the lecture series, we emphasize the fact that we are abstracting what goes on the CPU. In actual fact, the CPU itself is made up of additional hardware components. So it's not like your CPU will just have a control unit and an ALU. No, there are other additional components that we'll get to discuss later on, right? So things like multiplexers, for instance, right? These maxes you're seeing here. And you just don't have one multiplexer, right? You have multiplexers dotted around the CPU, right? It's not uncommon to have different ALUs. It's not like you'll have one ALU, right? You have adders there, right? You have register files. You have sign extend, right? Components, these are all hardware components that you find on the CPU. This was to, again, emphasize or underscore the fact that we are abstracting the execution of instruction. In actual fact, behind the scenes, when you're using a computer, there's so much that goes on. All right, I do hope you had fun reading up and studying about lectures about CPU instruction execution. If you're one of those who's interested in things like programming, especially low-level programming, you better understand this. Because in as much as you can actually learn how to write computer programs using a high-level language without going through an intensive computer systems or computer architecture course, if you're interested in doing some sort of low-level programming, you need to be able to understand these things, right? All right. I thought that was really interesting. So I don't know if there are any specific questions you have about lecture series number 7. Before I just give us a rundown of what to expect in lecture series number 8 and number 9. Are there any questions?
I have a question, sir.
Yebo.
In what instances is an instruction fetched from ROM?
Oh, so as you're booting the computer for the first time, you remember our discussion of the basic input-output system, the BIOS? The BIOS is a form of ROM, actually, although these days it's not classic ROM. It could be, I guess, programmable read-only memory or erasable programmable read-only memory. So in instances where you are working with instructions that are stored on read-only memory. So if you were to try and think of it from the perspective of your average computer, desktop computer or laptop, it will be as you are booting your computer, right? Because you're, at that point in time, your computer system is working with instructions, programs that are located on the BIOS. But also, if you remember our discussion of the different types of computer systems, lecture series number 3, where we looked at classification of computer systems, we made mention of the fact that specific types of computer systems will fundamentally make use of ROM, and specifically its most embedded computer systems. Yeah? So for instance, the example I always give is that ZESCO customer interface unit, right? That thing does not have RAM, it has ROM. So the instructions, it has a CPU obviously, right? It's a computer system, but the instructions are fetched from ROM. I cannot do what I can do with my computer to overwrite the current operating system that I have, for instance. I can do this easily with my laptop, but I can't do that with the ZESCO customer interface unit because the instructions are embedded within the hardware itself. Cannot overwrite them. I mean, with a little bit of effort, I suppose you could do that. I wonder if someone here would be interested in doing that. Now, I hope you're not one of those characters who's thinking of hacking the customer interface unit so that you start using ZESCO units for free, right? You become, I guess, an ethical hack or something. But so that's a classic instance of when you would want to, or when instructions would actually be fetched from ROM. Does that answer your question?
Yes, sir. Thank you, sir.
But here's the thing, right? Don't think of it in terms of ROM. Think of it in terms of memory unit. And a memory unit could be ROM, it could be RAM. And in fact, once we have a discussion, a firm discussion of computer memory, what you will realize is that on computer systems where, right? On computer systems where you don't have enough RAM, like Lighton here has 4 GB of RAM, but if you have a computer that has, let's say, 1 GB of RAM, there are like fancy techniques like there's what they call virtual memory, right? So you can convert some portion of secondary storage, which is cheaper, by the way. So some portion of your hard disk will be converted into what's called virtual memory, right? And so your CPU, your computer system will think that you have much more RAM than the 1 GB, which comes with the computer. If you seriously think about that, you could easily say, when you're making use of virtual memory, the instructions would be fetched from secondary storage because some portion of secondary storage will be converted into RAM, right? What I'm saying here is, ladies and gentlemen, what I'm saying here is that do not think of this thing we're calling memory from the perspective of, oh, RAM and ROM. No, it can also be secondary storage. So think of this memory component we're talking about to encompass everything here, I guess. Conservatively, I suppose, but I hope that answers your question.
Yes, it does, sir.
Okay. Are there any other specific questions? Maybe things that you were unable to understand as we were playing back the screencasts, portions of the lecture that need clarification, for instance?
So
what's usually hard for some of these lecture series we're having is they're not really practical. There's little we can do by way of practice here, right? The only thing we can do is we can simulate what would typically happen. So with that being said, you need to be imaginative, right? You need to be able to put yourself in a state of mind where you're able to visualize or to envision some of these things you're talking about, right? Make certain assumptions, right? Visualize what's happening here. Yes, sir. Somebody was about to ask a question.
What you're talking about virtual memory, is it what is called paging? Is it paging file?
Yeah. So in Windows, when you create what's called virtual memory, you behind the scenes a page file will be created on disk. So yes, but these things are referred to different things depending on the type of operating system that you are using. I do believe in Linux it could be called, I could be mistaken here. Is it swap memory or something? Could be swap. I don't know. Yeah. So yes. But that's in Windows. Are there any other questions?
Yes. So since you said CPU runs one instruction at a time, so then what about in the case where you're moving the mouse from one position to another? Is it that it leaves the process that it's doing, then moves to the mouse until it's done with it, then goes back to its initial processes? Yeah, I mean, so there's what's called scheduling here. And by the way, it's not like it's the hardware that's doing that, but behind the scenes, that's the role of the operating system, by the way.
So yes, the answer is yes. This is what happens. But the thing is, think about this for a second. Maybe this thing, I don't know if the imagination here, I mean, I don't know if it's too hard for people to kind of imagine what's happening here, but I'm just going to go to about system here. Think about this for a second. Look at my CPU, right? My CPU here is pegged at what? It says, according to the operating system, my CPU oscillates at 1.8 gigahertz, right? Now this 1.8 gigahertz means that at any 1.8 gigahertz means that my computer, in a given unit time, at a second, my computer processes 1.8 billion instructions a second. Is this making sense?
Yes, yes.
A second. Now pause here and think about this for a second, right? No pun intended here. if you are saying, if you are instructions per second, if you're saying you can execute 1.8 billion instructions in a given second, even if these instructions are executed one at a time, but because the oscillation is so fast, the computer gives you the illusion as though some things are being executed like simultaneously. So yes, the answer is yes. When you're moving the mouse here, behind the scenes, the operating system knows that, oh, Lighton at this point in time is using a whole range of, is interacting with the computer system in different ways, right? He has a bunch of software open, right? All these different pieces of software open. Not only that, by the way, when I'm moving the mouse here, I am implicitly using software, right? This is operating system here. So the answer, yes, is think of this. If we were to slow down the 1.8 billion oscillations here, if we were to slow them down, it would be like behind the scenes, what the computer system is doing is it gives the opportunity for the mouse, the software that's controlling, that's giving the illusion that the mouse is being controlled, to be executed, instructions associated with this, and then move to a different piece of software. Maybe it's Ocular, or in this case, I'm using K. Move to a different piece of software, right? But because it's happening at a relatively fast rate, you perceive what's happening as though it's happening simultaneously at the same time, but it's not happening at the same time. Does that help answer your question?
Yes, yes, thank you, sir.
But here's another thing, right? There's a plot twist here. Plot twist is modern day computer systems will have multiple cores, ladies and gentlemen. So if you have multiple cores, you can have different things being executed on those different cores, right? So even if we were to slow down these 1.8 billion instructions per second, because if you look at my computer here, I have two cores, I suppose, though it's dual core, so my software, my operating system thinks I have 4 cores. So you could view what's happening as being executed on CPU 0, CPU 1, CPU 2, CPU 3, or if you want, you can start from 1. So CPU 1 is executing instructions, CPU 2, CPU 3, CPU 4. Does that make sense?
Yes, it does.
Okay. Are there any other questions? Things that you think?
I have a question, sir.
Yes.
There's one thing I want to understand, something that is fascinating me about the stored program concept. On the idea that we've got a program and data loaded in a single memory location or in a single component.
Yep.
If I have a big file like a game, which is 20 GB file, and then my RAM is about 8 gigs. We are saying that only part of that game
you have to be a very rich person to have 80 gig of RAM, but yes?
Only small parts of my program will be loaded into RAM. Maybe small parts of my program will be loaded into RAM. Now I want to understand, in the case maybe of a game, then how how are the interactions between what is loaded in RAM and the files which remain in my secondary disk, for example, the data like music, graphics, and then only the instructions related to that game are the ones which are in RAM. Then how does the interaction take place? Is it
Well, so
again,
that interaction is determined by the programmers, right? So the programmers will know beforehand to say, realistically speaking, if you're designing a game, it's inconceivable for people to load the entire thing into RAM, right? It's not possible. And so this piece of software will be designed in such a way that the portion of the game, the software that is loaded into RAM, is related to, if we can use this phrase here, the stage of the game you are at. And really what's happening behind the scenes is that portion is just swapped into memory and swapped out. The relevant part is swapped out, the relevant part is swapped in. This is in fact what happens to your operating system. It's not like the entire operating system is going to be loaded into RAM. This is huge, right? It's just part of the operating system. Usually, I mean, the kernel, I guess, would be the part that will almost always be loaded into RAM. So the simple answer to that question you have is that the design of the software dictates which part of the software is going to be loaded into RAM. Now another way of thinking about this here, right? If you look at Ocular, for instance, this thing I'm calling Ocular is not just there for me to just I guess present or to view PDF files, but you notice that there are features where I get to annotate PDF documents, yeah? So assuming that this Ocular is too large to fit into my 12 GB of RAM on my computer, what would happen is only the part of the software that I'm using at that point in time will be loaded into RAM. The part that I'm not using will be left on disk. Remember, this piece of thing, this software we're talking about is nothing more than a series of instructions, these things here. Now, if it's a series of instructions, then it's a lot easier for you, it's very easy actually for you to determine which part you're going to swap into memory or swap out of memory. Does that make sense?
yes, sir. Thank you very much.
Oh, here's the thing, right?
Yes.
This is the other thing that people kind of misrepresent. This thing you're calling instructions, right? It's not like, so remember when you write software, right? When you write software, this piece of software will be, in a high-level language, it would be like add, 10, and whatnot. Let's say you have this, hypothetically speaking, another add, well, I guess, sub and whatnot. Let's say you have a very basic, not immediate, you have a very, okay. You have a very simple program that, that does, let's say, this is it, right? We're abstracting the instructions associated with this simple piece of software, which has 3 lines of code. As a human being, as a programmer, you perceive these instructions as being composed of these individual building blocks. Remember the building blocks we introduced during the short program concept, right? Building blocks, right? Instructions are used to build operations. Operations are what form computer software. Now, here's the thing, right? The computer, the CPU, it doesn't have the capacity or the capability to view these instructions the way you view them as a human being. As far as it's concerned, by the way, when it comes to MIPS, actually, it's a list of 32 bits for each instruction. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So in terms of, and again, we're simplifying this, right? As far as the computer is concerned, each of these individual instructions will be converted to ones and zeros. Now wait for it. 0, 1, 0, right? I'm just making this up, right? It's 1, 2, 0. Let's say these are the instructions associated with this is the machine code associated with instruction 1, 2, and 3. The computer doesn't see them as being distinguished separate like this. It sees it as a continuous stream of bits, like so. So in RAM, these things are actually stored like like if you remember, I responded to one of the emails to say, yes, there was a mistake and memory is contiguous, right? So these things, it's a continuous stream of bits, but there's a mechanism in place that allows you to distinguish one instruction against the other. The fact that instructions in MIPS, for instance, are represented using 32 bits. So if you know that each instruction is 32 bits, it doesn't matter if these things are stitched together, right? It doesn't matter because you can easily just split it up based on the 32 bits here. Okay, so I hope that answers your question. I know I went over and beyond here. It's always nice to go over and beyond the core of duty so that people understand. Are there any other questions people have about lecture series number 7?
Yeah, sir.
Yes.
So does it mean that once the computer goes off, then the sake of the fetching and decoding and executing programs stops, or
Yes,
it keeps
because
on learning?
no, it can't. It can't, because here's the thing, right? So think about this for a second here. We're saying the initiation process, right, of the instruction execution cycle begins where? It begins at the point in time when you're executing a piece of software. If you think about this for a second, now I didn't want to give this away, but I guess we might as well just give it away, right? It was going to be in the test, but I suppose we can always come up with another question. It's not that hard to manufacture questions in some of these courses. But if you think about this for a second, when you switch it off, nothing is running there, right? Think of it from a perspective of what sort of software is being executed when your computer is off. Nothing. The moment you switch it on, though, the first piece of software that is executed is what resides in the BIOS. Now, guys, if you want to understand what Kennedy is talking about here, there's a link, BIOS. There's a link on the Moodle where I walk you guys through, I don't know which machine this is, but it's a BIOS associated with one of my laptops. I think this is, this should be, oh, I don't know, this is my Lenovo, I suppose. So about the quality, but notice at this point in time, when I switch on the computer, right? What you're seeing here, the ThinkPad to interpret and Lenovo, at this point in time, the operating system has not been loaded, hasn't yet been bootstrapped. So the software that's currently running is the thing that is in the BIOS, or the BIOS itself, basic input output system, right? And so when you switch off the computer, nothing, right? There's no fetch, decode, execute cycle taking place. But the moment you switch on the computer, there's something going on, because you actually get to initially interact with the BIOS, which is software itself, right? Software that sits in ROM, anyway, in this case, or EEPROM, or I guess PROM, right? But when you switch off the computer, no, sir, nothing, no fetch, decode, execute happening there. Because the other thing to think about here is these are all interesting questions, I guess. We want to understand this. When you switch off the computer, remember what I said about this type of memory, especially RAM? It is volatile. What that means is that when there's no power being supplied to the computer, everything that is in volatile memory gets wiped out. It's gone. So when you switch off your computer, there's nothing in main memory, right? It's all gone. So you can't execute anything. I hope that answers your question. Hello? Oh, I don't know.
Oh, yes.
Okay, great.
Yes.
Any other? Yes.
So, yes, just in line with the question. What about when, in a case where the machine, the computer has been hibernated or been put to sleep?
Yeah, well, so I mean, that's an operating system feature that works in such a way that whatever is in RAM, I guess I'm speculating here, in certain instances, whatever is in RAM will probably be saved somewhere on disk, right? So that once you switch your computer back on, the stuff that's temporarily saved to disk is moved back to RAM, right? So it's a technique, right? It's a mechanism that you typically find in your average operating system that makes it possible for you to save the current state of the machine, standby, or I guess hibernate or something. I would have to, I don't want to misrepresent how this works. I don't know the specifics of the implementation, whether it's likely that the state of the machine is saved to disk somewhere. And really, there's nothing fancy here, right? It's all data, right? Everything is data. If you can save the data to persistent storage, whatever is in RAM can be saved to storage, so that when you restart your machine, when you start the machine back up, it recognizes the state it was in when you shut it down or something, or you put it on standby. And in fact, even better, some operating systems like my computer works in such a way that if I do a hard reset, right, if I just switch on, if I press the off key right now, there's a feature within Ubuntu that probably done something here that allows the computer to remember its state, leave and say suspend, for instance. You notice here, by the way, this answers your question. When I hibernate my machine here, when I suspend it, I'm suspending the state from RAM, so I'm saving it somewhere. But so my machine works in such a way that if I do a hard reset, it knows that something wrong happened. I did not properly shut down the computer. So behind the scenes, that state is saved somewhere, so that when I restart, some of the software that I was using, some of the data that I was working on will be recovered for me. Not all of it, but some of it. I don't know what the silence means here. Yeah.
So, sir, what you're saying is when it's in instance where it's put to sleep, so it just holds the processes that are in the background and the applications that you left running to store them somewhere.
We don't want to say processes here, but rather let's just say the data that's currently in RAM, right? Maybe that's a better way of putting it. Yes.
Yes, sir.
So those are stored somewhere. It's like you're just setting a state, and if you think about it, and I know the implementation is probably much more detailed than what we are making it seem. But if you think about it, there's nothing fancy happening here. If you have access to the data that you know is in RAM, and you suspend your computer, you just come up with an implementation as part of the operating system to say, when I suspend, save the state of the computer to disk. Are you not able to save a snapshot of, now this is nothing to do with disk, but I'm trying to underscore the simplicity of saving a state here. Is it not possible in Windows? It used to be, I haven't used the Windows in years here, but is it not possible in Windows for you to save the state, a snapshot of Windows? Is it not?
Snapshot means...
Well, so that in case something goes wrong, you can easily recover to the state that you know was safe or something. Like if your computer is, you normally save the state of the computer if you anticipate that you might be infected by a virus, for instance, right? If you constantly save snapshots, let's say every month or something, what you could do
are things like
yeah, exactly. So if you can do that, right? If you can do that, then what makes it hard for you to save the state of what's in RAM, to persist it to disk? It's not that hard. The only difference is you're not permanently persisting it to disk, because eventually, once you shut down the computer, that stuff will go away, right?
Yes, sir.
All right. Any other questions?
Yes, I have a question.
Yes.
My question is for computers, laptops that have
yes.
Yes, computers that have, let's say, 1.8 gigahertz running at 1.8 gigahertz, then they are saying they have turbo boost to 4.6 gigahertz. Is it that the turbo boost is always on for the gigahertz to run at a higher speed, or I don't really understand how it works?
No,
like
last time I checked, that's a theoretical maximum, right? So there's this idea, this notion referred to as I don't know if you've heard of clocking, right? CPU clocking.
Yes.
Yeah, so you can clock it, you can alter. It's a theoretical. It's a theoretical maximum of your computer. So what that means is you can stretch your CPU so that it oscillates at a much higher rate than the current configured value or something.
Oh, all right,
Yeah.
sir.
More questions? But these days, really, think about this for a second. These days, really, unless if you're performing computationally intensive tasks, right? And typically, I think it would be like gamers that would obsess a lot about doing this. But if you're using your computer for really basic things, like in my case, I mean, I've never seen the need to, well, I guess, I've never really seen the need to stretch my CPU to its theoretical maximum, right? I've never really seen the need, actually, never. Here's the thing, look at this, for instance, right? I think it has, I could be speculating here, but this maximum is what I'm talking about here. So you notice that currently it's 1.8, this is 1,817 megahertz, right? But it's 1.8 gigahertz, but the maximum is 4,000. I would like to, if I was to make an educated guess, what this means is I can stretch it further so that I can much faster rate than 1.8. So than this value here. The current value is 1.8, but because the maximum is 4,000, means I can stretch it further to 4 gigahertz. So that's what it means, really. That's a theoretical maximum.
All right, sir. Thank you.
Yeah, thanks. I'm concerned here. Someone here is saying, Mwandi, the truth is I don't understand what Mr. Piri teaches. I try by all means to pay extra attention, but nothing. And there's this very strange emoji here. I'm trying to help here, and I guess this COVID thing doesn't make life easier here, but I don't know here. Memory, do you want to ping me offline, and then we can try and see if we can make you understand portions that you don't understand? Sadly, right, what we're doing here, if you don't understand this basic, what we're looking at are the basic fundamentals, right? It's a precursor for what's coming. For you to be able to understand how the instruction set architecture works, how memory functions, you want to be able to understand these things we're discussing right now. So if you're struggling with something, there is nothing stopping you from sending an email to Lighton. Lighton.piri@unza.zm and tell Lighton, I'm struggling with this. How can I best understand this? Maybe I will direct you to a resource that would be perhaps much simpler for you to synthesize. I don't know, right? We are learning, so nothing from stopping you from just sending an email if you don't understand, if you're like memory. I don't know who agrees with memory here. Mondin, I don't know. But, here you go. Yeah, Chirokya is suggesting that you watch the Indian videos. And by the way, it's not just the Indian videos also. What you'll notice, right? What you'll notice, and this is good, classic stuff. What you will notice is, I'm not like a guide, but what you'll notice is that if you go on, if you go to what's tagged as the playlist here, right, that I've come up with. If you go here, what you will notice, ladies and gentlemen, is that this thing is arranged in such a way that there are other playlists that have nothing to do with the screencasts that I record. But these are videos that we feel will help people understand. Observe. I don't know if you figured this out, but observe. I guess if I click on this section here, all right, and I'm incognito here, so you have access to these things. If you go to, there we go, this web resource thing here. If you open on computer software, for instance, what you'll notice is that these videos that we've curated here, some of these are not prepared by Lighton. This is coming from computer file, which I don't know if it's meant for, I guess, level we're at right now, but explaining computers, these are things. So what I'm trying to say is, aside from what you're suggesting, what you can do is you can access these playlists that we've created for you. We've gone over and beyond here, right? There are a number of playlists here. There's a playlist dedicated to the von Neumann architect, the von Neumann model, right? It's here, publicly available, all these different things. There is a playlist dedicated to, I guess we haven't looked, peripherals is here, right? So really, TechWiki, by the way, subscribe to TechWiki, really interesting videos that will probably make it a lot easier for you to understand some of the things we're discussing, although it's superficial, right? But more superficial in comparison to what we're looking at. But so besides the Indian videos, these days, right? The vast majority of content that you find online is to do with computing. That's a fact. because most people that know how to I guess move around on the internet and to create content are people that have computing background. So you have a ton of resources online, really. The only I guess caveat I have here is you want to be selective in these resources that you're consuming, right? Which is why when you're viewing resources like this, for instance, you want to pay particular attention to these metrics here. Comments, and really check out the sentiments of the first couple of comments, whether they are positive or negative. The ratio of likes and dislikes. There are some videos that will have a lot of dislikes. It's a sign that maybe the person is talking about things that perhaps might misrepresent the topic being discussed, right? So I want to be careful about these things. All right, are there any other questions? I'm trying to see through the comments to see.
Sir, I have a question.
Yes.
Yeah, I've noticed that some memory sticks like RAM have frequencies. What does that have to do with the processing of information or instructions by the CPU?
Sorry, I wasn't paying attention. I was looking at the comments. Could you rephrase your question?
I was saying some memory sticks have got frequencies on them. Does that in any way affect the processing of instructions by the CPU?
No. That's not a frequency. That's a throughput. That's a throughput. That's so we discussed that. We discussed throughput and other characteristics associated with memory very, very soon. But it turns out that your typical. I'm trying to see if I can find a thumb drive on my desk here to see if I can give a realistic example here of what I'm talking about. But when you're accessing data on a memory stick, what you're doing is you're fundamentally moving. Think about this for a second, right? You, if you, let's say we are here, right? You have a memory stick, which is this, right? Memory stick, external memory stick. You are connecting that memory stick to the computer as what? As a peripheral, right? Think about this for a second.
Yes.
The thing is, the data that is on this memory stick would have to be moved depending on what you're doing. If you are reading from a memory stick, data is moved from the memory stick. If you are writing to the memory stick, like if you're saving a file, data is written to the memory stick and read from the memory stick simultaneously. And so there is usually a value that's associated with how fast you can read and write data from that memory stick. That is called the throughput, right? So it's not nothing to do with the frequency we are talking about in relation to the CPU. Or I was trying to see if I could.
Or maybe let me just try to. Maybe I misquoted. What I meant when I said memory sticks, I meant the actual RAM.
Okay.
Yes, some actual RAM have got frequencies. For example, the Novo ThinkPad I had has some numbers, and then there's a frequency to say 1.333 gigahertz. I don't know if it's megahertz or gigahertz at the end.
Yeah, but here's the thing, right? And again, we discussed this in memory. Oh my God, this so this thing here, right? Look at this 1.8 billion I was talking about. That frequency could be anything. When we're talking about instructions on the CPU, the 1.8 would be this would be, I guess this would be the rate at which instructions for the CPU, this would be instructions. If you're looking at memory, the oscillation you're talking about is in relation to the, I guess you could be it as the data, right? So it's how can I put this? It's still the throughput could be anything. Throughput could be the rate at which data is being moved around, the rate at which instructions is being moved around on that component. It could be anything. Throughput could be the speed at which, if Lighton takes, when I cycle to work, if Lighton takes 15 minutes to go to Unza, right? And we know that Lighton knows that Unza from where he lives is 4.6 kilometers, and it takes 15 minutes. You can convert this into a value, right? You could view that as height as well. It's a throughput. It's just a rate at which something is being done here.
No,
Do you understand? Yeah. So this would be, so what you're looking at, the RAM you're talking about is, I guess, the rate at which both instructions and data can be transferred from memory, in this case RAM, to the CPU. Now you notice here that there's two different things, right? There's what you're talking about is the rate at which you can move things from RAM to CPU, right?
Yes.
And then what I was talking about in relation to the CPU is the rate at which instructions are executed here on this thing here. Those are two different things here. The 1.8 gigahertz is in relation to the CPU. What you are referring to is the rate at which data is transferred in between CPU and main memory. And this is interesting, really. Maybe we can incorporate this once we discuss main memory here. You notice that that the value that you're talking about determines the rate at which, or how fast your computer is, right? So it's not just the rate at which instructions are executed here, but how fast you can transfer things from RAM to the CPU. Because, like it or not, these instructions will have to be transferred to the CPU at some stage. And the transmission here introduces some sort of latency, right? Because you're moving things through so-called buses here, those wires. And so there's time here, there's time wasted when you're moving things from RAM to CPU. So anyway, what you're referring to is the rate at which things are being moved from here to the CPU, essentially.
So would it be best to have a CPU and then these RAM memory chips that are of equal frequency to fully utilize the instructions to be instructed?
No, you wouldn't be able to. You wouldn't. I would be surprised. Now I'm speculating here, but if there is memory that oscillates at the same rate as the CPU, then it's damn expensive, right? Usually, the CPU oscillates at a much faster rate than the data transmission from RAM. And in fact, it makes sense, right? What you're doing here has to be done at a much faster rate than you're moving things from RAM. Yeah? Think about this for a second. So in an ideal case, yes, I guess people would want to have a situation where the rate is the same, the rate of transmission is the same, I guess, but that's almost impossible, really. It would never be the same, actually, because there's still latency introduced here also. So, anyways. Okay, any other questions? Hey, also, I'm looking at the time here. By the way, we're thinking of experimenting something else. I was going to mention this towards the end of the term, but beginning next time, I think we'll start having more live lectures instead of offline lectures. I want to see what sort of mode of interaction people prefer. So instead of dumping those offline screencasts, maybe we'll have live lectures, right? How does that sound? I don't know. Yes, no, yes.
Sir, maybe you can just confirm before you continue.
Okay.
Yeah, I've been having some difficulties understanding the machine cycle, specifically at the decode and execution part. Yes, in the screencasts there, it's a bit different to notice when you've switched from the decoding and execution, because some instructions, like in the example you've given, the first instruction is just to load the number. So after the CU has decoded that, it's a bit difficult for me to maybe track how it has already even executed it and also move to the next one, the next instruction. I don't know if you can shed more light on that part.
Yeah, I'm struggling to understand what you're trying to put across here, which is why I want to open up the lecture notes here, so that try and see if this would be much easier to understand. But okay, so come again. Which part are you finding hard to understand? I'm guessing you're referring to this part here, right? These things, are these things you're talking about?
Yes.
should be that, yes, sir.
But so what exactly is hard to understand here? I'm trying to figure out which
On on executing the second and the last instruction, I was trying to like write notes on how these instructions are being executed. But when I noticed the second and the third one, I don't know if it's the third one is a bit more explained than the second one.
What do you mean it's a bit
I don't know
more
if that makes sense.
No, it doesn't make sense. I'm struggling to make sense out of this. So we have these 3 instructions, right? Which
Yes.
This is just an example, by the way. So which of these you're saying is there's different instances. We're doing the same thing over and over again.
Yes.
Instruction number 1. Instruction number 2. Instruction number 3. The instructions might be different, but they're all going through the same cycle. Fetch, decode, execute. Fetch, decode, execute. Fetch, decode, execute 3 times. Now, the only difference here, if you think about this, if we can be superficial here, the only difference is in the execution, what the ALU will do, right? Loading will probably involve like a different type of execution. Adding is different or something, because adding might involve compounding what's in the accumulator, in this case with the new value, right? Storage will involve some sort of write back to memory. So, but explain which part is a bit confusing for you.
I think you've already explained. From just what you've said, you've shed more light, because yes, I was hoping for maybe the second and third instruction. I noticed a certain difference that you've just noted to say the accumulator is being used in one of them, and then in the last one it's not.
Yeah, think about this for a second, right? This could just as well have been another add instruction, by the way. It doesn't matter. This could have been an add instruction, right? All of these could have, if it makes life a lot easier, what you should do is assume that all of these are add instructions, where you're just adding things that are, of course, one of them has to load, I guess, so that maybe let's just assume that all of these, okay, let's assume something is already in RAM and you're just adding everything. All of this could have been add instruction, in which case you're just adding up numbers in the registers, right? So I guess in this case, it would be like we're adding 1 and 9 or something, 1 and 9 and whatever was in the accumulator at that point in time. This could have been anything. This could have been subtract instruction. The key thing here is to just understand the process. What's happening when you fetch an instruction, right? What happens when you fetch an instruction, when you decode an instruction, when you execute? What is happening? Which components are involved? That's all. I'm glad that we were able to shed more light. Are there any other questions?
Yes, sir.
Yes.
There are times when you delete a program, then there are certain programs that you can use, like to restore the same program. Even after, does it mean that the program still remains on the hard disk? Or maybe where does the program go? Because it's very possible for you to restore it again.
When you do what?
For example, you delete a game. Then later on, you want to restore the same game, but you don't have the resources to download it again. So you get a restore program to bring it back. Does it mean that the same game is always on the hard disk, or what happens?
Well, normally the way operating systems work is it's a safety mechanism. When you delete something on your computer, unless if you do a shift delete, or if you're on the terminal, you just you do an RM command. What the operating system will do is it will move it to, on Windows, and I'm not sure if this is still the case, but there was a so-called recycle bin, right? It's moved somewhere in a safe location, right? So that you can easily restore it if you want to. So I don't know if this answers your question, but.
So not in the recycle bin. You even cleared it from the recycle bin. It's gone. It's literally gone from the recycle bin. And then
no, that's not. I don't think that's possible.
You delete a file, or even let's say, for example, photos. You delete them permanently. There are some softwares that enable one to restore the files that are permanently deleted. So does that mean
Yes.
the residue files that it left, that's what it uses, or just somewhere in memory?
Yeah, it's just the way
It
hard
might be
disk work,
cache.
right? I think no, they're misrepresenting cache, and now you're talking about something.
It can't be.
So, sorry.
Maybe it's in the restore point somewhere there.
Yeah, well, I mean, so if you're talking about the restore point, that's completely different, right? So the thing here with the restore point, right? Good point, by the way. But the thing with the restore point is it's a saved state of the computer. So imagine what I'm doing right now. At this point in time, my computer I have saved what? I have data and instructions amounting to 393 gigabytes. If I was to save the state of the machine at this point in time, I save it now. Tomorrow, when I delete files and I end up with, let's say, 100 GB, I can easily restore the machine to a point in time when I had 393 GB, in which case I'll have access to the files that I would have deleted tomorrow. I don't know if this is what you're referring to. So yes, Philip, thank you for your comment. If this is what you guys are referring to, I don't know if it was Leand or something, then it is possible if you save the state of the machine for you to restore that data again. I don't know if this is what you're talking about.
Right.
If not, is it or is it not?
It kind of agrees with the question because recently I deleted the files a month ago. Then last week I used some software to bring back the same file. So maybe
would have to look
not.
at again. Would have to try and figure out exactly how that piece of software works. Maybe if you want, you can reach out to me offline. I mean, I can take a look at the piece of software, and then we can try and see if we can figure out how it works, and then we can share thoughts with the others. I don't know. I can only speculate. I have no idea which piece of software you're talking about. No clue which operating system or version you're talking about. So, but these are important questions to ask.
All right. I'll reach out.
Yeah. Alice, I don't know what you mean here by saying explain much on register with reference to CPU cycle. I don't know what you mean, Alice. Do you want to say a thing or two about what you're talking about here? Because we are spinning the head. People are about to leave here, so I don't know. Alice, do you want to explain a bit more about what you're talking about? The types of registers I thought were clearly outlined in the. If you notice, there's a reason why this walkthrough here, we didn't look at just one instruction. We have 3 instructions, and you know these different 3 instructions. The same thing is happening. It's like Sisyphus here, right? Same thing is happening. Changes to the PC, same changes. MR, MBR, MDR, current instruction register, accumulator, same thing. The only thing that's changing is the instructions. Right? PC points to the next instruction to execute. MR gets a copy from what was previously in the PC. MBR has a copy of the actual instruction being pointed to by the address stored in the MR. The current instruction register has the actual instruction that being executed at that point in time. The accumulator has partial results or temporal results of the execution by the ALU. It's not that hard now, is it? I'm struggling here. I don't know, maybe anyway. I'm going to have to suggest, Alice, you can reach out in the sideline to send me a private email, and then I'll try and see if we can make you understand this further or something. Are there any other questions, pressing questions before we part ways?
Just one. So we're hearing rumors that we might open next year. Do you think that it might be true?
Well, I don't know. I'm not part of Senate. The information that you have access to is the same information that I typically would have access to. The only thing I would do here is, what do you mean open next year? We're open. We are still open right now. What are you talking about? Sorry.
No, as in, sorry. Let me rephrase it for us, the first years.
Or maybe face-to-face
learning.
learning.
Back into campus. They're coming back into
But the answer is on our website. You don't have to rely on rumors. Have you seen the revised sessional dates here. Have you seen, do you see what's happening when we come back to term 2? On the 27th, what does it say?
Online face-to-face lectures for regular students, 15 weeks.
Okay, that's one part. The other part is, if you go back to, this is our information, this is public knowledge, by the way. Don't rely on rumors. Rely on information that is coming through from reputable entities. In this case, is almost always information that is circulated, reopening here. If you look at the most recent announcement, the only people that are coming back for face-to-face interactions is 4th years for undergraduate and postgraduate students, and a few selected students enrolled into certain programs. Like I think I remember seeing people from mines or something, but everybody else will continue with this sort of mode of interaction here. Right, so you notice all postgraduate students, they came back this weekend. So I don't know about that rumor, but to the best of my knowledge, can you hear me?
Yes.
Hello?
Yes, sir.
Yes.
Yeah.
Yes, we can get
my,
you.
my machine just froze, and yeah. So to the best of my knowledge, we for anyone other than 4th year students or students that are going to be graduating, you are going to continue, or we are going to, because we are stuck in the same boat with all of us, right? In God. So it's online lesson throughout here, sadly, for now anyway, but I'm sure, I mean, it's not like things are set in stone here. It's possible that the landscape might change, right, very, very soon, in which case maybe you'll be told to say you can report back for lessons or something. But this is here. It's here. It's in the revised session dates, where the online sessions for 1st years all the way up to 3rd years, and then face-to-face for postgraduate students and 4th years. It's here. You want to develop the habit of regularly accessing the website. There's usually a lot of interesting information, the important information. If I were you, I would, yes, it's coming, wait for it, bookmark the website. But you don't want to bookmark the website. No, you don't. Okay. Great. So, friends, I'm going to log off now. I'll leave you to your what do you call this? Your gossip and whatnot. And then I'll see you next week. Quiz on Friday. I think we have a session next week where we get to, I don't know if it's next week or after next week, where we get to discuss lecture series number 8 and number 9. And then the other week we have just a brief recap on what to expect in the test the following week. All right, so if there are no questions, cheerio, stay safe, and see you when you see me online. Bye.
Bye, sir.
Guys, these things,
Before we go further, chiringa. Stop the recording.
so that we know.